Here we want to do an example with constant acceleration in 2 dimensions. We have a pair of deflector plates. See, an ion is traveling very quickly with speed v. When it enters halfway between 2 deflector plates separated by width w, and it enters parallel to those plates. The plates have length L, and while between the plates, the particle experiences an acceleration perpendicular to the plates. Once outside the plates, the ion is a distance d from a detector, where we know that d is much larger than L, the length of the plates, and w, the width of the plates. How much was the particle deflected once it reaches the detector? Well, where to start with this? Well, always a picture. So we have a pair of deflector plates. They have length L and width w. So we have this particle, it has some speed v, and it enters halfway between the plates parallel to the plates. Then, while inside the plates, it experiences a deflection. There's an acceleration perpendicular to the plates, which gives it a slight displacement as well as a component of the velocity that is now perpendicular to the plates. So it's now pointing at an angle. Then it's a distance d away from detector, and so it propagates now at this new angle in uniform motion until it hits the detector, at which point it will be deflected some amount y from where it would have hit had there been no deflection. We need a coordinate system, so I've chosen for my y-axis the 0 of the coordinate system to be at the initial point y position of the particle, and then positive up, and I've chosen the 0 of the x-coordinate system to be at the point where it enters the plates and positive x to the right. To understand what's going on, let's take a closer look between the plates. So here's the 2 plates with the center line in gray. So some particle enters with some horizontal velocity. And then it's going very fast. So while it's in here, it's deflected just a little bit. And when it gets to the end, it has experienced some small deflection, delta y, as well as gained a vertical component of the velocity, delta v. We were told that it's very fast, the distance in here is very small compared to the distance it travels after. Whenever you see something like that, an expert problem solver is going to think to themselves some sort of simplified approximation. Can I use those to simplify my problem in some way? If it's not in here very long, does that mean I can set the change in velocity to 0? Or maybe the change in position to 0? Well, I certainly can't set the change in velocity to 0, because that is what's going to give us this deflection. With that small vertical component of the velocity traveling all the way to the screen, that's what creates this large deflection at the end. However, this small displacement doesn't propagate. It's a small correction to the deflection that occurs at one time, but one time only. So it's possible that we would be able to neglect this amount of displacement to be able to solve the problem more simply. We're going to look at it both ways, but I wanted to point you out that when you see things like this length is much, much larger than some other length, you should be thinking about ways to use that to make your problem easier. So I've brought my other picture back. What sort of physics applies to this problem? Well, we have 2 regions of constant acceleration, but I gotta tell you, graphical method speaks to me for this problem. I want to know the total displacement in the y direction. I have one region of constant acceleration in the y direction, and then no acceleration. I want to look at the velocity graph as a function of time. So here's what that looks like. The velocity, this is just the y component of the velocity. It starts out at 0, but it gains some velocity in the y direction while it's between the plates, and then it's constant for the rest of the time. Note the 2 key times, t1 and t2. t1 is the time it exits the deflector, and t2 is the time it hits the detector. And now the total deflection, which is the total displacement along the y-axis, is going to just be the area under this curve. So the first thing I need to do is to find the maximum component of the velocity in the y direction. We know from the graph that's just equal to the acceleration while in the deflector times t1. You can get that from the constant acceleration equations, or just look at the rise over run in this graph. The acceleration is the slope of that graph, and the rise is the maximum velocity, the run is t1. And so the total area is equal to the area of that triangle, which is 1/2 base times the height, t1 times vy, times the area of that large rectangle, area 2, which is vy times the time difference, t2 minus t1. Now you should recognize that this area here, A1, is exactly that small delta y that we were going to ignore before. It's the amount of displacement that took place inside the deflector, and A2 is the displacement outside the deflector. When we talked about ignoring this because it was small, that's the same as saying that this area A2 is much larger than A1. And we can see if that's going to be the case. The key is we need to find the times. Well, we can solve those in terms of the things we know because we know the x component of the velocity from the beginning and all of the distances. In fact, if we just look at the figure, the equations are trivial. That first length of the deflector, that distance, is just the velocity in the x direction times t1, the time inside the deflector. And then this second distance, d, is just the x component of the velocity, which is v, times t2 minus t1. So now I can use these to solve for the time, to substitute into there, and we'll solve for everything immediately. So I've brought back all those relationships and noted that the total deflection, the quantity that we're interested in finding, was the area under that curve, which if we make the approximation where we ignore the deflection inside the deflector itself, it's just that second area, A2. Well, we can substitute that in. So y, which is equal to A2, is equal to v sub y, which is a times t1, times the time difference, t2 minus t1. And now if I just use these relationships to substitute in for t1 and t2, and I can multiply that out to find the answer. The acceleration times the length of the deflector times d, the distance to the screen, divided by v squared, where that was the original horizontal component of the velocity. And just to check, I put in all the units, meters per second squared for acceleration, meters and meters for L and D, and then v squared in the denominator would be meters squared over second squared, and those cancels out to give me meters, so I have some confidence what I have is right. And in my approximation, I'm done. But let's say you're uncomfortable with that, and you want to find the total deflection. Well, that's fine, because the exact expression, I might put EX for exact, is just the both of those areas combined. And that's really not that much harder. Remember that delta y that we found when we were looking at the deflector is just that first area, the area of the triangle, in our velocity versus time graph. So I substitute in v sub y is just a sub t1 times t1. That's, of course, 1/2 a t1 squared, which is just from the constant acceleration equations itself. I substitute in for t1, which is L over v squared, and now we have the total displacement. So how much did this area under the first curve, the deflection inside the deflector itself, really matter? Well, to take a look at that, I'm going to show you a couple tricks. The first thing I'm going to do is I'm going to multiply that second term by the d over d, which is the very large distance outside the deflector. I'm doing that because I know that's going to be large compared to L, the length of the deflector, and I want to find ratios of those two terms. Now I can factor out an A times L times D over V squared from both terms, and once I do that, the first term is just a 1, and factoring all of that out of the second term, I'm left with the 1/2 as well as an L and a D in the denominator, L over 2D. And remember, we were first given that D is much, much greater than L. So if D is much, much greater than L, L over D, then is much, much less than 1. This is really true, then this should be a good approximation and you recover what you had originally. Either way, it's not too hard to solve exactly using graphical methods, but I also wanted to show you that when you have systems where you're given some parameters are much larger than others, try to find ways to use that to simplify your problem.